A. Ramos, R. Mesquita, and C. Gonzalez, and the presenter is Paulo Piloto. You can read his CV because we are running a bit late, and you can start now. Thank you very much. All right. Okay. So we can bypass that. Thank you.
Thank you. So the title is Temperature Analysis and Validation of Porcelain Case Beams Submitted to Elevated Temperature. I want to say that my research is devoted to the effect of fire on structures. So this is the outline of the presentation. So I will begin with a short introduction. I will show you the objectives and motivation. I will move for the experimental tests. I will do a short description of the tests. I will talk about the specimens, instrumentation, and the results. And after that, I will show you the numerical validation of a model, talk about materials, the results, and finally the conclusion. So, porcelain case beams are mainly built with two or more different materials, normally steel and concrete. Usually they are built with I-shaped or ash-shaped steel sections filled with concrete between flanges. They can also be constructed from thin-walled built-up sections. We can manage different cross-sections, design solutions may be used, so we can change the stirrups, the studs, the reinforcement of concrete, and so on. And the elements were cut on the floor, and once the concrete has cured, beam is as a composite, meaning 2 or 3 materials, and the stirrups were positioned along the length of the beam, as you can see here, the preparation of the specimens, and the resistance of the steel section is increased doing this. So we expect to increase the stiffness of the element, and also an important characteristic is that we increase the fire resistance of the elements. So we decided to do some experiments on these kind of elements, and we are motivated to present some new and original design formulas to be included in the Eurocode. So to do that, we need to characterize the behavior, the thermal and mechanical behavior of the elements. And of course, this paper deals with the thermal behavior only. And we need to characterize the temperature that is imposed by our heating device. And we do the tests at different levels. I know that this is not fire, this is a kind of constant temperature, but this is the way that we need to do it, because we decided to present design rules, and to do that you need to see what happens at different temperature levels. Of course, we did more experiments using the fire standard test, but this paper only presents the results for 200, 400, and 600 degrees of imposed temperature on the upper and bottom flanges of the elements. So from the start of this research, since the year 2005, only a small number of experiments under fire conditions or under elevated temperatures were reported. And according to Eurocode 4, that is devoted to fire design for steel and concrete structures, this Eurocode presents only a kind of a tabulated method with certain and very few conditions. And the simple calculation method for this kind of element is not well developed. So Eurocode do a kind of approximation using the results for composite beams under certain conditions also. And we decided to understand the ultimate limit state of these kind of elements, and of course the load bearing capacity under bending tests. And our research we think that our research will provide the essential data for the calibration and validation of the new simplified design methods that we are doing. So I'm going to present you the results of 12 tests. This is only a part of a more general study of 27 tests. So I'm going to present, I decided to divide the tests in 4 series, as you can see here, for different temperature level. And we decided to do 3 tests for each series. And each specimen is identified, as you can see, by the length and the length between the support of the element, the length between the load points here, and the length exposed to elevated temperature, LF. Okay. So this is the typical setup that we decided to use. So tests were prepared to determine the bending resistance at elevated temperature, 2 different slenderness beams. So I decided to use 2.4 meters and 3.9 meters. We decided to use also simple supported beam with 2 supports and 2-point loads. As you can see here, this is the load system, this is the support condition. And of course, there is a length that we decided to call it LF, and this is the length exposed to high temperatures. So the test was defined in 2 stages. So first of all, we decided to heat the specimen and leave the supports with free expansion, and then we adjust support after the temperature achieve almost constant temperature level on the beam. So the heating device was kind of this machine with 70 kilovolt ampere of maximum power, and we delivered a heating rate of 800 degrees per hour. To increase the thermal efficiency and insulation was used, and the specimens were protected by a kind of a ceramic, as you can see on the right side of the slide, and the temperature was almost constant after a certain period or certain target of time, and this is our second stage. Almost constant temperature level. So for target temperature of 200, I need 15 minutes to achieve this temperature level, and more, and of course more time to stabilize the temperature of the element. As you can see on the picture on the center, you see the element, and of course the electroceramic devices that we use, and on the bottom and on the top of the beam. Let's talk about the specimen. So the IP100 skill profile with classified according to this number, and the concrete used the silicious aggregates and was classified as C20. And we decided to use this kind of cross section, as you can see here, the longitudinal reinforcement, the tubes, profile and concrete. And we space every 167 millimeters the position of tubes. Tubes were partially welded to the longitudinal steel reinforcement. This is important also. This was welded. So that here I can show you the series 1 and 2 and 3 and 4. Of course, they have different lengths. Let's talk about instrumentation. So we decided to use some thermocouples. Some of them were spot welded to the steel profile, and the others were, as I say here, welded to a small steel washer encased in concrete, as you can see on the right, on the picture on the right. So, of course, we have also used some spot welded to the steel profile to control the heating process of the beam. Now I can show you some pictures. On the left, the deformed shape mold of the beam just at the end of the test. And on the right, you can see when you remove this insulation mat fiber material, you can see that the temperature, of course, is not uniform all on the length of the beam as we expected. But we decided to, as you can see here, there is a big gradient of temperature, but this is the location of the end of insulation, so that's why we have this kind of temperature field. So temperature was recorded in both stages, so the unsteady stage, the first stage, and of course the second, which I mean the steady state. And this is the unsteady, the stage 1, and this is the stage 2. As you can see, temperature was recorded in 5 different main sections, and the results, are presented only for section S2. I mean, this is the temperature in steel follows the trend of heating rate. I mean, this is a constant trend of 800 degrees per hour, and the temperature in concrete presents the traditional effect of moisture, and temperature is almost uniform on the cross section, as you can see. For each experiment, I show you some of the experiments, not all. You can look on the paper for all the results. Here you can see the temperature distribution along the beam length, as for sure. We have 5 sections where we decided to measure the temperature and control heating. So you can see that the temperature length of the heating zone is smaller than the total length of the beam. So we are talking about 52% and 70% of the total length. Of course, the insulation here support is not efficient, as you can see, and that's why the temperature drops on near the loading point of the beams. More results and a short video on the left on what happens to the beam and the temperature evolution near the load point, as you can see here. This was taken with infrared thermography. Now let's go to numerical validation. So this is a simple model. We have a different, more accurate model, but we decided to do it as simple as possible. So we decided to use this kind of plane element. The model is the element has linear functions, linear integrating functions. So the model was refined to best convergence with the solution of experiments. And 3 cases were selected for 200, 400, and 600, prescribing the experimental heating curves. So the exact experimental heating curves that we measured during the tests. We decided to use perfect contact. We have different models with non-perfect contact, of course, but this is important to show you that this kind of model is sufficient to predict. So I'm going to pass this slide because this has to do with the behavior of material with high temperature. And finally, we can see on black we have the experimental curves. On green we have the numerical results, and on the red curve, on the red curve I have only one because it represents the maximum temperature difference between experimental and numerical results. Okay, so we have a maximum relative error of 14%, 5% during all the heating stages, so first and second stage. Okay, so 18%, 12%, and so on. So the time series results were resisted for specific nodes according to the points of each thermocouple position. So let's present some discussion of the results. So there is an evidence of good agreement between experimental results and numerical results. The maximum temperature difference between the experimental measurements and numerical results was also identified for each material, for steel and concrete. The numerical simulation validated the time required to achieve the steady states. This was an important value that we need to know, because we need to decide how long should we keep the system running for achieving the constant temperature level. So some small difference between numerical results and the experimental measurements were detected, and may be explained by the boundary conditions, of course. And the numerical model also used perfect insulation, while the experiments present some residual heat loss across the ceramic fiber insulation material. We decided to use perfect contact, which can modify the heat flow between steel and concrete. And of course, the material properties were not measured, so we assumed them from our references. And finally, the conclusions: the thermal analysis of 12 experimental tests was presented. 2 meeting stages on torsion case beam were simulated. The temperature was measured in 5 different cross sections, which allowed analyzing the heating thermal effect along the length of each beam. The nonlinear transient finite element analysis was used to validate results, and numerical simulation was also used to predict the time required to establish the thermal steady condition in the second stage. And a good agreement was determined between experimental and numerical results. Finally, I want to acknowledge the material support from the following companies, and this concludes my presentation. Thank you.
The paper is open for discussion and comments and questions, polite questions, not comments. Please. Any questions? I would like to ask you about this experimental curve. Where did you measure the temperature?
Where did I measure?
Where? To establish.
Okay, I'm sure.
Where did you measure the temperature? To establish the. This is very good work, because everything was measured and very good. But.
Well, in this slide, I can show you the positions where we did measure the temperatures.
The temperature.
Yes.
So you had the whole history.
Yes.
That's our clarification.
Of course, we decided we have more results, some mechanical results, but in this paper we decided to use only the thermal results.
Any other questions, please? In that case, you have a question? In that case, we can thank the speaker. So go to the next paper.